This is the third and last installment in our three-part series on filter design. And in this module we will look at the major filter design techniques available to engineers today. Now, we won't have time to look at the nitty-gritty details on how these routines produce the filter coefficients that you will then use in the filter structures that we have seen in the previous module. But we will review the characteristics of the transfer function and of the frequency response produced by these routines, and the method to put them to use. These routines are available as pre-canned functions in most numerical packages, such as MATLAB, for instance, and hopefully this review will give you a map to navigate the various possibilities that will be available to you when you tackle a signal processing project. And welcome to Module 5.10 of Digital Signal Processing. This is the third and last part in our three-part series on filter design, and we will tackle the problem of designing a filter from a set of specifications. So first we will review what we mean by filter specifications, and then we will briefly describe some IAR and FIR filter design techniques. The purpose of this module is not to examine the details of each design technique, but just to inform you of what is available in the form of numeric packages that you can use to design your own filters. So let's review the filter design problem, and suppose you are given a set of requirements, such as a frequency response specified in terms of where you want the pass band to be and where you want the stop band to be. At the same time, you could have multiple stop bands and multiple pass bands. You will probably have some phase requirements as well, namely in the form of whether linear phase is necessary or not. And most often you will have some limit on the computational resources you can use. We are interested in realizable filters, therefore our final design will be expressed in the form of a rational transfer function, and our problem becomes finding the degree of the numerator and of the denominator, as well as the coefficients of the polynomials involved, in order to best fulfill the requirements. So, for example, if we want to design a low pass, the specifications could be like these. We have a cutoff frequency, we have a desired value for the pass band, and a desired value for the stop band. Now, these specifications seem to indicate an ideal characteristic that we know we cannot attain in practice. And therefore, we will try to fulfill these requirements by taking explicitly into account what we know about what is achievable with a realizable filter. In particular, we know that the pass band and stop band transitions cannot be infinitely sharp, and therefore we will use some transition bands to allow for a gradual decay of the frequency response from pass band to stop band. Also, the magnitude response cannot be constant over an interval. We will see shortly why. And therefore we will have to specify some tolerances over the pass bands and stop bands within which we allow the frequency response to move. In general, the lesson is the following. If we want very small transition bands, we will need to use a filter of high order. And similarly, if we want small error tolerances, we need a high order filter. Now, high order means a high polynomial degree either at the numerator or at the denominator of the transfer function, which means that we will need to use more computational power to implement that filter, and that the delay introduced by the filter in a causal realization will be larger. We can plot the realistic low-pass specifications graphically as follows. Instead of having one cutoff frequency, we have a transition band between a frequency omega p, which specifies the end of the pass band, to a frequency omega s, which specifies the beginning of the stop band. And instead of having one desired value for stop band and pass band, we have tolerance regions within which the frequency response can wiggle. The fact that we cannot have an arbitrarily sharp transition from pass band to stop band should be sufficiently clear. The transfer function is a rational transfer function, and as such, it cannot have a discontinuity point. The reason why we cannot have a flat response, i.e. a response that is identical to a constant over a certain interval, maybe requires a little bit more of an explanation. So again, we start from a rational transfer function, and now suppose that the frequency response, h of e to the j omega, is constant over an interval, no matter how small that interval. Well, in that case, the z-transform will be constant over an interval as well, and therefore we can write that the denominator minus the constant times the numerator is identically 0 over an interval. But this guy here, b of z minus c a of z, is a polynomial in z. So if it is constant over an interval, it has an infinite number of roots over that interval. But we know from the fundamental theorem of algebra that if a polynomial has an infinite number of roots, it is identically 0 over the entire complex plane. Which means that if the Fourier transform is constant over an interval, no matter how small that interval, it will be constant over the entire frequency range. As a consequence, you can think of the frequency response of a filter as a shark. It must always move and it can never be at rest. An important case is what we call the equiripple error, where the error, for instance, in this case in the passband, oscillates between a maximum and a minimum, and the local extrema of the frequency response coincides with the upper and lower limit of the tolerance region. Once the specs are in place, the three big questions are, well, first, are we going to design an IIR or an FIR? And once we have answered that question, how will we determine the coefficients of the transfer function, and how do we evaluate the performance of the filter? In order to answer the first question, we have to consider the pros and the cons of one design versus another. IIRs are computationally efficient. They can achieve a very strong attenuation in the stop band rather easily, and they're good for audio because they can achieve a monotonic characteristic in the passband. On the other hand, they might have stability issues, especially in numerical implementations that are prone to overflow or underflow. They're difficult to design for arbitrary responses, namely a low-pass or high-pass characteristic is easy to obtain, but it's not so easy to obtain an arbitrary response with an IIR, and they have nonlinear phase. FIRs, on the other hand, they're always stable, they can be designed optimally, as we will see later, and they can be designed with linear phase, which is a great advantage, especially for communication systems. On the other hand, they're computationally more expensive, and acoustically they might sound harsh sometimes. In general, finding the degree and the coefficients of the polynomials involved in the transfer function is a very hard nonlinear problem. In the case of IIR filters, there is a vast body of literature on filter design that dates back from the days of discrete electronics that has been converted to the problem of designing digital filters. FIR filters, on the other hand, are purely digital entities that do not exist in the analog world, and so design techniques for FIR filters have been developed from scratch since the beginning of digital signal processing, and they have reached their apex in the early 70s with Parkes-McClelland's optimal filter design technique. Let's begin our survey by looking at some IIR design techniques. So filter design was an established art long before digital signal processing came around, and lots of nice designs were developed along the years using discrete electronics. There are some methods that can translate analog designs into rational transfer functions. We will not look at the details of these methods, but most numerical packages, such as MATLAB, provide you with ready-made routines that will help you design filters according to this classic template. The design often involves a trial and error phase. You specify some parameters from the beginning, such as the type of filter and the desired cutoff frequency, and then you guess other parameters, usually the filter order. You run the routine and you verify that the provided filter fulfills the specs. If that is not the case, you will probably have to change and increase the filter order until the specs are met. Let's now look at a few classic filters mutuated from the analog world. We will concentrate on a low-pass prototype, but be aware that design techniques exist for high-pass and band-pass as well. The first filter we will look at is the Butterworth low-pass. The Butterworth filter has a magnitude response which is maximally flat, and it is monotonic over the 0-pi interval. The design parameters are very simple: the order of the filter and the desired cutoff frequency. You run the algorithm and you get a prototype filter. You test the filter with respect to the width of the transition band and the passband error. If any of these parameters do not fulfill the specifications, then you increase the order and you run the algorithm again. The frequency response of the Butterworth filter looks like this. It is, as we said, a monotonic curve that decays smoothly from 0 to pi. This is an example of order 4 with a cutoff frequency of pi over 4. The Chebyshev low pass has a magnitude response which is equiripple in the passband and monotonic in the stopband. The design parameters are the order, the passband maximum error, and the cutoff frequency. So we have one extra parameter with respect to the Butterworth. We run the algorithm and we check the result against the specs with respect to the width of the transition band and the stop band error. If any of these parameters do not fulfill the specs, we increase the order and we run the algorithm again. The frequency response of a Chebyshev filter looks like this. Here we have again order of 4 and cutoff frequency equal to pi/4, and we specify a maximum passband error of 12%. Since the desired value is 1, this amplitude here is 0.12. With respect to the Butterworth filter, we have a steeper transition band, and this is the reward for accepting an equiripple error in the passband. Finally, let's look at the elliptic low-pass filter. The elliptic low-pass filter is equiripple both in the passband and in the stopband, and the design parameters are the order, the cutoff frequency, the passband maximum error, and the stopband minimum attenuation. We run the algorithm and we check the result in terms of the width of the transition band. So you see, this design lets you control all the parameters of the filter except the transition band. So it's the most complex of the three. The frequency response looks like this. And again, our order is 4, the cutoff frequency is pi/4, and here we specify a maximum passband error of 12% and a minimum attenuation of 0.03. So this is 0.03 and this is 0.12. The elliptic filter gives you the steepest transition band for a given order of all the filters we have seen so far. Let's now look at FIR design methods. FIR filters, as we said, are a digital signal processing exclusivity, and so are the algorithms to design them. In the case of FIR filters, the rational transfer function is no longer a ratio of polynomials, but just one polynomial in Z. So optimization procedures do exist that can achieve optimal results for a given set of specifications. In the 70s, Parkes and McClellan developed an algorithm to design optimal FIR filters that yields filters with linear phase and that have equiripple error both in passband and stopband. The algorithm proceeds by minimizing the maximum error in passband and stopband of the transfer function. Linearity of the phase is achieved by designing an impulse response which is either symmetric or antisymmetric. We end up with 4 types of filters according to whether the impulse response is even length or odd length, and symmetric or antisymmetric. Type 1 filters, probably the most common, have an odd length impulse response, and they are symmetric around the center tap. Type 3 filters have an odd number of taps, and they are antisymmetric around the center tap, which imposes, of course, that the center tap is 0. Type 2 and Type 4 filters are symmetric and antisymmetric filters respectively, both of which have an even number of taps. That means that the center of symmetry of these filters falls in between samples, and so they both introduce a non-integer linear phase factor of 1/2 sample. Let's look in more detail at the phase properties of a Type 1 FIR filter. A Type 1 filter is an odd-length symmetric FIR, so it will look maybe like this, where the taps are symmetric around an index capital C. The symmetry relationship can be simplified if we shift the filter so that the center tap falls in 0. So we define an auxiliary filter h' of n, which is simply h of n plus capital C. And this filter now will be centered in 0 and symmetric around 0. We can express that by saying that h' of n is equal to h' of minus n. The relationship between h' and h in the Z domain is simply multiplication by z to the minus capital C. If we now compute the Z transform of h' of n, we have the sum for n that goes from minus capital M to M of h' of n times z to the minus n. Because of the symmetry, we can isolate the center tap, h' of 0, and then write the rest of the summation by collecting equal terms. And so we have the sum for n that goes from 1 to capital M of h' of n that multiplies z to the n plus z to the minus n. If we now replace z with e to the j omega,
we get the Fourier transform of h prime, which is simply h prime of 0 plus this sum for n that goes from 1 to capital M of h prime of n that multiplies e to the j omega n plus e to the minus j omega n. But we know that this is simply twice the cosine of omega n, and so we obtain that the Fourier transform of h prime of n is purely real. And this means that the Fourier transform of h prime of n is zero phase. We can get the Fourier transform of h of n as simply the zero phase Fourier transform times a linear phase factor e to the minus j omega c. So we have proven that type 1 filters do indeed possess linear phase. A similar proof can be carried out for the other three types of linear phase FIRs. Let's now look at the Parkes-McClellan design algorithm, also known as the minimax filter design algorithm. The magnitude response of the filters designed by this algorithm is equiripple both in the passband and the stopband. The design parameters are the order, which in this case corresponds to the number of taps. We also specify the passband edge, omega p, and the stopband edge, omega s. So we specify the width of the transition band, and we specify the ratio of the passband to stopband error, which we call delta of p over delta of s. Note that we're not specifying the absolute error, which means we can weigh the importance of the error by privileging the passband or the stopband. We run the algorithm and we obtain a filter that we have to check against the maximum passband and stopband error specified in the requirements. If the error in either band exceeds the requirements of the specs, then we have to increase the order and run the algorithm again. The frequency response of a minimax filter looks like this. It's a typical equiripple characteristic, and you can see that the extrema of the frequency response all touch the edge of the tolerance regions, both in passband and stopband. This is designed for a 9-tap filter with a transition band between 0.2 pi and 0.3 pi. We can increase the number of taps to 19 for the same transition band, and we can see that we get steeper transitions and lower errors in passband and stopband. And we can go up to, say, 51 taps. We get something that is actually quite good, with very small error in passband, almost undetectable error in stopband, and steep transitions. A good way to compare the performance of different filters is to express their magnitude in decibels. So if we say that G is the maximum magnitude in the passband, the attenuation of a filter expressed in decibels is 20 times the log in base 10 of the magnitude of the frequency response divided by the maximum gain. With this notation, we can plot the frequency response of the fourth order elliptic low pass, and we can see that it has an attenuation of about minus 30 dBs in the stopband. A comparable FIR filter, comparable in the sense of computational cost, is the 9-tap minimax. And we see that for that computational cost, we get an attenuation that is definitely less, because it's on the order of 10 dBs, approximately. To get a performance comparable to the elliptic filter, we have to increase the length of the filter to 19 taps at least, and here we hit the approximate 30 dB mark. The 51-tap filter that we saw before has actually a very, very good attenuation. It's about 90 dBs. But of course the price we pay is non-negligible in terms of the number of operation per output sample. Finally, as mentioned before, we just concentrated on low-pass prototypes, but of course we can use any of these designs to obtain bandpass and high-pass filters as well. Optimal FIR bandpass and high-pass filters can be designed directly with the Parkes-McClellan algorithm. You can also design optimal FIR with piecewise linear magnitude responses, so something that, for instance, goes like this. The literature on filter design is really, really vast, and we just scratched the surface. It is a very fascinating topic that has occupied researchers for very many years and keeps them occupied to this day.